Welcome to an AQA is chemistry video on particle fundamentals and mass spectroscopy. I'm thinking whether or not to make this a two-part video or not. So if this ends up being a two-part video, expect it to be like that. If this ends up just being a one-part video, then well, it will all be here. So I'm splitting the video into particle fundamentals and mass spectroscopy. I'm doing both because particle fundamentals is pretty much anything you know from GCSE. I'll go on to really electron configuration, really understanding atoms a bit later, but just the basic things like, for example, here's an atom of beryllium, as you know from GCSE. You have your neutrons. Should I colour this in actually? As you can see, beryllium as an atom, you have your atomic number, which is your atomic number is just the number of protons, which is 4. As you can see, beryllium has 4 protons, and its relative atomic mass is the number of protons and neutrons. Everything, you know this from GCSE anyway, but as you see, that's 4 plus 5, 9, and then your electrons, as you know in the shell, 4 electrons, 5 neutrons, 4 protons. Obviously, and then there's isotopes. Isotopes are the same. It's an atom with the same atomic number, the same number of protons, but a different number of neutrons. So an isotope of beryllium, you can have beryllium 10, right? So 6 neutrons instead of 5. So this, you should already know this from GCSEs, but in case you need a small reminder. So I'm gonna go straight into mass spectroscopy. So I did a previous video on mass spectroscopy, and but that was more about reading the graph, but understanding the graph. But this is more about now how mass spectroscopy actually works and why things are done in a specific way. So workings of a mass spectrometer. The mass spectrometer is split into 4 stages: ionization, acceleration, ion drift, and detection. So this is how a mass spectrometer actually looks like. Obviously, I haven't got the real one, but it looks like this is just a diagram of it. But this is how it relatively looks. In fact, this is the one's better because it shows you the pathway, the stages, and so I'm going to be using this as a reference as I come through each section. And yeah, so ionization is the first stage. The first step is ionization of the sample, and the main techniques are electrospray ionization or electron impact ionization. So electrospray ionization is a gentler technique and prevents fragmentation. And what it is that it's typically used for polymers and biological materials like DNA. The reason for that is I'll explain later, but the sample, how it's done is where you get the sample and you dissolve it in a solvent, and a high voltage is applied to that. So I'll start again. You get your compound and you dissolve it in this solvent, and then once you've dissolved your compound in the solvent, you apply a high voltage. The high voltage will rip a proton off of the solvent, and it will attach that proton onto your compound, and that makes your compound positively charged. Your sample is now positively charged. In when you're doing electrospray ionization, the reason why this method is the benefits of having this method is that there's less fragmentation of your compound, so you can use for compounds like DNA or any specific polymers that you don't want to fragment. So that's useful for that reason. And now the other method, which is the one I have in the example here, is called electron impact ionization. And the sample is first vaporized and is passed through a nozzle, which is a thin tube. So it's actually passed. This is much bigger one here, but it's usually a thin tube that's passing your compound through, right? And then when that happens, you have what happens in electron impact ionization is kind of in the name, but the sample is first vaporized as I said before, and then it's passed through a nozzle, and it's hit with electrons with an electron gun. So an electron gun is just a coil of wires, but it beams electrons off, and those electrons knock off electrons from the molecule, and the molecules are now positively charged ions because it had electrons knocked off from the molecule. So as you see it, this is your gas, your vapor gas, and your electrons have now been knocked off your molecule compound. So now it's a more positively charged molecule, and that now can go to the next stage. So the molecules are now positively charged ions, and this method, but the problems with this method is that it causes fragmentation, and so that's you're not getting a pure product. You're not getting an entire product as you had it initially. So that's a problem that you could probably have. The second stage is acceleration. I say acceleration and deflection, where molecules are accelerated and they all have the same kinetic energy. That's a very important part here. No, that's bad. This is important because there is an exam question where you have to work. It's a 6-mark question that usually comes up in the exam. It's a calculation question, and you need to understand this principle when you go to answer it, and I'll explain a bit later on. But from the standard equation, you know that so all these compounds have the same kinetic energy when they're accelerated, right? From standard equation, Ke equals half mv squared. That's the equation for kinetic energy. All molecules have the same kinetic energy, therefore the speed is dependent on the mass of the molecule. Lighter particles move faster and are detected before heavier particles. But the ions are then deflected, so I have it here. They're accelerated, and then these are kind of like ions. The ions these are kind of like magnets here, and they cause the ions to be accelerated. And then when the ions accelerate, they reach this point here, which is another electromagnet, but it deflects them, right? And I'll go on to explain that one there. So the ions are deflected by a magnetic field according to their masses. The lighter they are, the more that they'll deflect. The more they're deflected, and the amount of deflection also depends on the number of positive charges on the ion. So how many electrons were knocked off at the first stage. So just to sum up what I was just saying there is that they accelerated here and they all have the same kinetic energy, but the speed that they're going at through this stage here is dependent on the weight of that compound. So lighter compounds will be moving slower when they're accelerated. However, all compounds will still have the same kinetic energy. When they're deflected here, heavier compounds will be deflected less. It's more to do with something like called momentum, but don't need to know too much about that. But also in the ones that have lighter compounds will be deflected more. At the same time, compounds that have that are more positive charge will also be deflected more, because this is a negatively charged magnet. If these are more positive, they'll be deflected more. That's what you need to understand from that part there. Ion drift. So the third stage is ion drift, and the time of flight is given by distance over velocity. So time, you guys know your equation. V equals distance time. If you want the time, distance over v. Just rearrange that. And this formula, this leads to like an equation for the time travel that depends on the mass. So if we know, So this is what I meant by you need to know this equation, because, well, you need to be able to rearrange this, because this question, they'll give you a question like saying this compound has, they'll say something along the lines of, you have a compound and they want you to find out the how long the tube is, and they'll give you all the information and they have to rearrange the equation. They'll tell you the mass of the compound, and so this is only a first stage. I'll do a better example in another video, but for example, you need to be able to do this at least. Ke equals half mv squared. This is the bare minimum, right? But if we're talking about finding out the time, if time is equal to distance over the velocity, we can find out the velocity from this. We have the velocity here. Rearranging this, that ke over a half, that's like 2 ke. Anything over a half is the same as timesing it by 2, dividing it by m, and then if you want, that's equal to v squared. So the v is equal to the square root of 2 ke over m. 2 ke is just a notation. It's just energy, so it'll be 2e over m. So you might see it like that, but I sometimes write that, but 2e over m is energy, so it should be a capital E there. But time, we're not done yet, that's just the velocity. The time, remember time, alright, so the time, we're not done yet, so the time is equal to the, or it's equal to, as I said before, distance over your time. Sorry, over your velocity, my bad. Your distance over your velocity, right? We have a velocity now, and you have a distance. So time of flight is equal to wherever your distance is. We'll just write out distance over 2 ke over m, which can also be written as, and the way you'll see it in your exam, time of flight is equal to your distance multiplied, if this is on the denominator, I can just flip these over, multiplied by, if you know maths, you can just know that that's just the way it works, m over 2 ke, or e, whatever. But that is your equation for time of flight. If you really need to rearrange it, so and so. But right now, I'll go through an exam question on a later video, but this is just gonna go through the basics of it, and then we'll see from there. So lighter ions take less time, as time is dependent on the square root of m after ion leave the electric field. So what I was talking about before about the ions, lighter ions taking less time, because the smaller the mass, according to this equation, we can actually explain what we mean via this equation, that the smaller the square root of m, the smaller the time, therefore less time is taken. Likewise, the higher the value of m, there's nothing square root, just m in general. If m increases, the time will increase. If the mass increases, the time increases. If the mass decreases, the time will decrease. Proportional, directly proportional way. And then the last stage of mass spectrometry is detection. And in detection, the ions will hit a negatively charged plate, which causes a current. Actually, I can explain the last stage before. So, as I said before, when we're talking about the square root of m, or m, if m is higher, during this stage, then it will take less. It will take more time to reach the detection plate. And if m is less, it takes less time to reach the detection plate. And here's the detection plate here. So I'm going to go through the last step here. In detection, the ions hit a negatively charged plate. It has to be negatively charged because our ions are positively charged. So it needs to come and hit this here. And when it does that, the reason that's one of the reasons, but the main reason for this is that it does that because when it hits this negatively charged detector, it induces a current, and the size of the current gives a measure of the size of the molecule hitting the plate, and that in turn also gives us tells us the abundance of the molecule. So this is the part that actually allows us to interpret and identify the type of compounds we have and its abundance. So that's how a mass spectrometer actually works. I'm now going to move on to analyzing analysis of this of identifying a molecule. So once you've identified your molecule, you need to be able to analyze what it all means. So once the sample has passed via the mass spectrometer, data can be collected to identify the molecule. The spectrum produced, as I said before in the previous video, once the sample has passed through the mass spectrometer, a spectrum is produced by the spectrometer on the spectrum. And if you want to watch my previous video and like how I actually explained how to read one, then that's better. But this is going to be a brief summary of what I said in the last video. The x-axis will be the mass to charge ratio, and the y-axis is the percentage abundance. The main peak, so the spectrum will produce lots of peaks, but the most important peak is the molecular ion peak, and this is the peak of the greatest mass to charge ratio, and this represents the mass to charge value of the molecule being analyzed. So it's not the highest peak, it's the furthest to the right of your graph, so the highest x value. So the mass to charge ratio, the peak that's furthest away from the center or from zero, or furthest away from your y-axis, essentially, that is your molecular ion peak, and that number will represent your MR essentially, or it represents your mass to charge ratio, where it actually is the mass to charge ratio of your compound that you're analyzing. So if you get the molecular ion peak at 90, you know the MR of your compound is 90. Isotopes. So smaller peaks will cluster around the molecular ion peak, and these are from the same molecules but with different isotopes in them. The isotopic molecules have different masses and so different mass to charge ratio values. So as I showed before, I already told you what an isotope is, and so around as you've seen in the previous video, I had the graph with the I had the graph with the mass to charge ratios and the abundance. And if you looked at actually where the molecular ion peak is, there's a lot of little small clusters of peaks near the molecular ion peak, and those little peaks are different isotopes. So you can have carbon 13, for example. That's an isotope of carbon. The molecule you actually have is the same. It's the same molecule, but they're just isotopes of that molecule. So if you see those like little peaks, that's what it actually represents. There's also the majority of the other peaks are fragmentation. This is something that we generally try to avoid, but they happen. Fragmentation, any smaller and significantly lighter peaks in the spectrum are because of fragmentation. So the molecules, what fragmentation is that your compound is broken down. So if I had let's just go propane, right? Propane. During electron impact ionization, there are other reasons why it could fragment, but for example, in electron impact ionization, the fragmented version of this would be just any form of it being broken down. So 2 plus and a CH3. That's a fragment. It all could just be all CH3 plus, CH3 plus, and then CH2 plus. That any form of a broken version. That's what fragment. Imagine fragments of glass. It's just a broken down version of glass, right? The molecules can fragment into the spectrometer, as I said before now. So analysis to calculate. So this is just one of the calculations, but there's another calculation that you need to know. But this is one of the calculations that you also need to know. But the other calculation I said before about the time of flight, that's a much longer calculation. I'll do in a different video. So once we've passed the mass spectrum, we can calculate the AR, which is the RAM, or the relative atomic mass. Relative atomic mass is the average weight of the mass of the atom relative to carbon-12. The key word here that you need to answer is average. That's the most important one. That's the most important thing to understand there. That's going to come into when we're talking about this equation of working out the relative atomic mass. And this is because its value is calculated taking into account all of the isotopes and their relative abundances. Using the spectrum can be used to view all of the different isotopes and their relative abundances. So isotopic mass is along the x-axis, and isotopic abundance is along the y-axis. So I'll draw out this part. I'll draw out this part a bit later on in the video. But the actual equation that you need to know in order to work out the relative atomic mass is the sum. This is just the capital sigma, in case you didn't know this, but this just means the sum. If you already know this, actually, you should know this from GCSE. Yeah, the sum of isotope abundance multiplied by the isotope mass number over the sum of the isotope abundance. Right. You can calculate that the AR or the RAM, since we have all the isotope masses and their relative abundances. So example of a calculation, for example, if I had boron, which boron has two. This is how it actually works. So you have in the exam you get 2 or 3, however many isotopes that they want to give you of that compound, and I'll tell you that it's abundant. So boron has 2 isotopes, boron 10 and boron 11. The spectrum from data shows that approximately 20% of the boron is boron 10, and 80% of the boron is boron 11. And from this data, the RAM can be worked out as, using this equation, it will be 80%, which is 0.8 times by 11, plus 0.2 or 20% times by 10, and that equals 10.8. And if you go into the periodic table, as I had before, I have left on the periodic table. Yeah, here it is. If you go to the periodic table and you go to boron, it should be roughly 10.8. Yeah, here you go, actually, 10.8. And that's how you actually got that value. And so I said before I was going to draw you if I can actually find my ruler. There you go. Right. So the graph will actually look like this. Alright, so this would be lost. So this is the graph that you have here. So you have your percentage abundance on the y-axis, and on your x-axis should be your mass to charge ratios. Mass to charge ratio. And then you have The only two that we have here have 10, maybe a line graph like this, and 11. We're told that 20%. You don't have to actually draw this out, but this is what you'll be given. You look at in the exam, you get a diagram that looks like that, and a diagram that looks like that. And so they give you this information, and that's how you get answering this question. Say you see 80% here for isotope with the mass to charge ratio of 11, which is just MR of 11, and another one with 20% for an MR of 10, 10 times by 0.2, or 11, and sorry, plus 11 times by 0.8, and that'll be 10.8. Isotope abundance. So the abundance can be quoted in many different units, percentage, for example, and if an isotope abundance is given as a percentage, the calculation becomes slightly easier. So as long as all the isotopes have been considered, sum of all the percentages must always equal to 100%, must always add up to 100%. So summing, I've got so many typos here. There's probably more, but anyway, the point being, summing the percentages is, as I've shown you before, you need to know the equation. The isotope abundance multiplied by isotope mass number, and that's all over the sum of isotope abundance, which is just going to be 100%. So you could just do, for example, 11 times by 80 plus 10 times by 20 over 100 equals 10.8. But at the end of the day, same thing really. Just cancel each other out. The denominator will always be 100%. In this case, it will always be 100%. And this is the case the majority of the time. So there could be a situation where it's like a 99%, but you're not going to get that exam. You're going to use this equation where it's going to be that this part here is 100%. That's 100%. And if it isn't 100%, then you had something wrong, because in the exam they're not going to give you a situation where it's going to be 99%. And in saying that, that's it. The video's done. Hopefully this is going to be a one-part video.